Our next unit is about trigonometry, but before we get to that, we're going to look a little bit at similar triangles because everything in trigonometry is based on a concept about similar triangles. So this is something you may have done before, but it's a good review. Triangles are similar if all the angles between two given triangles are the same. So for example, in this number 3 here, this smaller triangle is similar to the big triangle if this angle is the same as that one, and this angle is the same as that one, and this angle is the same as that one. The first thing you're going to have to do in Chapter 6D is to prove that triangles are similar, to show that they're similar. And you do that by showing that all the angles are similar. So if I'm going to do that for number 1, I would first want to label the angles so I have something to refer to. So I might call this point A and this intersection B, this one C. My computer catches up to me here, then this one D, and this one E. And here I actually have two triangles. It looks like one triangle with a line through them, but if I split them up, then I have a smaller triangle. Let's call that ABE. And then I have the bigger triangle, which is then ACD. And so sometimes it's helpful to split them up like this and see which triangle you're referring to. So now I can show that this angle and this angle have to be the same. So angle BAE equals angle CAD. And why are they equal to each other? Well, angle A is equal to angle A. It's the same angle. So I can write down it's the same angle. Okay, now I can look at the other angles. If this is a right angle, as shown in the diagram that's given to us, and this is a right angle, then I can also say angle BEA equals angle CDA, because they're both right angles. That information was also given to you, so you could also say that was given information. And once you've shown two right angles, then these angles here also have to be equal to each other. Put a little tick on them to show that that's a different angle than these ones. These two angles also have to be equal to each other because the angles of a triangle always add to 180. So if angle A and angle E add to a certain number, that's going to be the same as angle A and angle D. And when then I subtract that from 180, I'll get the same number for B and C. So I can conclude here as well that angle ABE is equal to angle ACD start here. Once I've shown that two angles are the same, then I know that the third angle is going to be the same. So I can from here say, therefore, triangle ABE is similar to, use a little curve, a little S on its side, to see is similar to angle ACD, triangle ACD. Notice that I'm always writing the letters of the various triangles in the same respective order. So if I write ABE on this triangle, then I always do ACD on this triangle, because this angle matches this one, B matches C, and E matches D. Okay, let's do one more example. That was number 1. And if I also look at number 3, this is similar kind of thing, but the triangles are turned around. One of them is not in the same orientation as the other one. So when I do the comparison of the angles, I have to make sure I'm looking at the triangles in the same order. I'm going to do the same thing as before and label them. doesn't have to be A, B, C, D. You could also use other letters. But A, B, C, D are just the beginning of the alphabet. And if I compare these, then it's angle A matches angle D, and this B here is actually going to match with E. So if it's helpful to you, you can rewrite the triangles in the orientation that you want to compare them. So this is A, B, C, the first triangle, and then if I flip the other one to match it up to this one and put this long line here, then this top E is going to match with B, so I would write E here. And D is at the bottom. And then it goes out to this part where they cross, that's C. So that'll help me make sure I compare the angles in the right order. Over here, I've got right angles again, so that's going to be easy to compare. And then this angle is equal to this angle. If you remember your properties of triangles and parallel lines from an earlier math class, then these are equal to each other because they're called vertically opposite angles. Anytime you have a construction where you put two lines on top of each other like this, the angles that are opposite each other are always equal. So those two are equal and these two are equal. And that's called vertically opposite angles. So that's what we're going to use there. Okay, we set up our proof to say angle. Let's do the right angles first. BAC is equal to angle EDC because they're both right angles. And then I can say angle ACB, and now we have to be careful. We want to write the next one in the same orientation. So if I started with A here, then that corresponding angle is angle D. So angle D, and then out to C, and then up to E. Yeah? You can see that on the drawings nicely. If I do ACB, then that's going to be DCE going in the same order. And those are equal to each other because they're vertically opposite. Vertically opposite angles. Vertically sounds like it should always be up and down, but that's just a historical reason why that got called that. So even if the angles are not up and down from each other, we still call them vertically opposite, just because they're across from each other in a special way. Okay, therefore, I've shown two angles, so I can assume that angle B is going to be equal to angle E as well, because the other angles are all equal. So triangle ABC is similar to ABC, so DEC. And the triangle sign, triangle DEC. Okay, just one last comment. There are different ways of showing angles. I've shown them by always putting an angle on the outside and then putting it in order with the angle I'm interested in the middle. But there are different ways of doing that. If it's really clear on the triangle which angle is which, then you can sometimes just write angle A, if there's only one possible way of angle A being read. Here on this triangle, though, that would have been tricky for angles B, for example, because angle B has an angle going this way and it has an angle going this way. So which one do you mean? There it's important to give the starting point and the ending point of our angles too. Right? ABE tells me I'm doing this way for angle B. And if I had wanted this angle, then I could have done CBE to indicate this angle. Right, so we always include where the angle came from and where it's going to help make sure we don't confuse it with other parts of the diagram. But if it's really clear, like in this diagram here, it's pretty clear which angle you mean each time, except for maybe C, you'd have to be careful, and you can shorten it to this. Another way of doing it that tends to be used in IB diploma courses is to put the angle sign on top like this. So that shows you where it's coming from, where it's going, but also the angle sign is up top instead of on the outside. So there are different ways. As long as you're consistent with whichever way you use, you can do it in any of these ways. Okay. There are other formations of angles that use parallel lines in their proofs. We're not going to focus so much on these because we're headed to right angle triangles with trigonometry, but just to quickly show you, if I have parallel lines here, then this angle is equal to this one because of corresponding angles on parallel lines. And this angle is the same for both triangles because I have this little triangle and this big triangle. So that's how I can pull the proof there. This angle is equal to this one because they're the same angle, and these two are corresponding angles on parallel lines. This is another situation. Here again we have the vertically opposite angles to give us 1. And then this angle is equal to this one because of alternate angles on parallel lines. So using parallel line rules, we can come up with a lot of other proofs for similar triangles as well. But it's number 1 and 3, those two examples that we'll be focusing on. Once we know that two triangles are similar, there are lots of problems that we can solve that involve the sides. There's a special property of similar triangles. If the angles are all the same, then the ratios of corresponding sides will be equal to each other. That sounds a little complicated, but let's back up and talk about it in another way. Similar triangles are basically enlargements of each other. This smaller triangle, if I enlarge it, I get this bigger triangle. It's like taking a picture and making it into a bigger format. The proportions of everything have to stay the same. So whatever I've multiplied this side by to get this longer side, I will multiply that by the same ratio, the same constant of proportionality to go from this side to this side. So we can use that on these similar triangles by setting up ratios. Remember in this format that this is equal to this, and this is equal to that. Didn't write in the right angles, but those are right angles. And this one is equal to this one. We'll need to know that to set up the ratios properly. So here I look for two ratios that I definitely have. This side is related to this side, so I definitely have the 4 centimeters and the 9 centimeters. So first look for one that you have, and then look for one that you're trying to find out. If this is related to this, and then this side is related to this one, there's the x I want to know. So I'm going to set up a ratio between these two sides and make it equal to the ratio between these two sides, and then I can solve for x. So let's start with the x on top, that's always easiest, and say x is to 5. So there's my ratio. Remember, I can put ratios in different ways. Usually we've learned ratios as double dots like this, but I can also set them up as fractions. So this is the ratio set up as a fraction. Okay, so x is to 5. Now I have to make sure I do it in the right order. X came from the bigger triangle, so I want the side on the bigger triangle to go on top. X is to 5 as 9 is to 4. Then I have equal ratios, and I'm going to use cross multiplying and dividing to find x. So I multiply both sides by 5 and multiply both sides by 4. And then those 5 cancel and I have x over here. And if I multiply both sides by 4, then I have 4x equals 9 times 5, which makes 45 on this side. Divide both sides by 4, and I get x equals 45 divided by 4. If I'm dealing with measurements like centimeters, then I can go into decimals. So 44 divided by 4 would be 11, and 1/4 left over, 1 over 4 left over is 11.25 centimeters. Okay, so x is equal to 11.25 centimeters. Now I want to go and find y. So I'm going to put y on top and then figure out what it has to relate to. So y on this triangle relates to 6 on the other triangle. So y is equal to 6 as, and now we look for something I can compare it to. Again, 4 and 9 I have. Always go back to ones I'm given. Even though I know 11.25, it's best to go back to the ones I'm given. So 4 is on the same triangle as y. That goes on top. And 9 is on the same triangle as 6. So that one goes on the bottom. Cross multiplying gives me 9y equals 24. And then I do y equals 24 divided by 9. Could use a calculator up to this point, but I'm going to simplify it using fractions. So 24 divided by 3 is 8, and 9 divided by 3 is 3, and 8 divided by 3 is equal to 2 2/3, so I get 2.67, rounding off the repeating decimal to 2 decimal places. Okay, so y is equal to 2.67, and x is equal to 11.25, and there I've solved all sides of the triangle. Okay, I'm not going to do another example, but I'll just give you one warning for this type of example. Be careful here that if you're given sides like this is 2 centimeters and this is 7 centimeters, make sure you know what's referring to what. So if this is 2 centimeters and this is 7 centimeters, then that side for the big triangle is going to be 9 centimeters. That becomes especially important if one of them is a variable. So if this is x, that when you use that side in a ratio, you don't call it x or 2, but you call it x plus 2. And so you might have your ratio with x plus 2 is to something, right, equal to something over something. So just watch out for that kind of example. Okay, you're ready to do the exercise 6D from your unit outline.